The universe, a grand symphony of light and darkness, began its journey approximately 13.8 billion years ago. That is the story we are often told, a captivating tale of a single point, scorching hot like the core of a dying star, infinitely dense, where everything, the vast expanse of space, the flowing river of time, the shimmering matter, and the surging energy burst forth from a profound void. However, deep within the hearts of physicists, the guardians of the cosmos's secrets, this story always carries a crack, a haunting whisper, that something remains incomplete. Mathematics, the pure language of the universe, shatters under its weight, and the laws of physics dissolve into an uncontrollable chaos. Over the decades, we have built a tower of understanding about reality on shifting sands, clinging to a narrative that seems only the tip of a submerged iceberg. But now, in the year 2025, as light from the most distant stars is captured by the James Webb Space Telescope, bringing vivid images of primordial galaxies, a new horizon is opening, challenging every assumption you have ever held. Before that scorching Big Bang, there was a frigid, boundless realm where the universe whispered ancient secrets, awakening in us a profound awe, an emotion that resonates like the first gaze at a star-filled night sky. If you have ever felt your heart stir before the mysterious beauty of the cosmos, if the stars seem to call your name in dreams, prepare yourself. We are about to embark on an inspiring journey where science not only explains, but also ignites faith in the wonder of existence. In 1927, Georges Lemaitre, a Belgian priest with a scientist's burning soul, painted the first picture of the universe's origin, a picture that made the world ponder. He traced time backward, following the expansion of galaxies, to a singular point, a moment where everything contracted into nothingness, with infinite density in temperature. As if the entire universe were compressed into an invisible grain of sand, mathematics screamed in agony. This is impossible. Albert Einstein, the giant of physics, whose mind changed how we perceive reality, frowned and called the idea bizarre, something not harmonious with the balanced beauty of the universe he envisioned. But the evidence was undeniable, arriving like stars emerging after a storm. Edwin Hubble, through his telescope, observed galaxies racing away from each other at dizzying speeds, as if the universe were an ever-stretching fabric, carrying secrets of a dramatic origin. Reversing time, everything converged to a single point, a point that shakes the mind with its grandeur. But here is a truth rarely spoken aloud, a whisper full of emotion in the halls of science. Einstein's masterpiece, general relativity, the theory that helps us understand black holes swallowing light, time bending around planets, starlight curving in graceful arcs, completely collapses at a singular point. The equations divide by zero, spitting out infinity's fatal signs in physics, indicating that your theory is broken, like a beautiful bridge, unable to bear reality's weight. Imagine dividing 1 by a number growing smaller. 1 divided by 1 is 1. 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. As the denominator approaches 0, the result shoots to infinity, and at that exact point, mathematics stops working, leaving a haunting void. That is the profound tragedy of the Big Bang singularity, a tragedy that makes us pause and reflect on the fragility of human knowledge. Nevertheless, scientists still tell this story with fervent belief. 13.8 billion years ago, the universe exploded from nothingness, giving birth to space as vast as an endless ocean, time flowing like an eternal river, and everything that exists from stardust to glittering galaxies originating there. But in late-night debates, under the dim lights of laboratories, they admit another truth, one full of emotion. The singularity is a sign of a missing piece, an invitation to deeper exploration, a reminder that the universe is always grander than we imagine. Stephen Hawking, along with Roger Penrose, proved this in 1970 with a theorem both elegant and cruel, like a sad poem about human limits. If general relativity is correct, the singularity is unavoidable, and the universe must begin from an inexplicable state where all laws vanish. This is heartbreaking, making us tremble, the theory that perfectly describes black holes devouring light, satellite orbits enabling positioning on Earth, starlight bending in graceful curves, fails at the universe's birth moment, the instant everything began. Scientists try to avoid it, focusing on what happened after the first trillionth of a second, the formation of atoms from scorching plasma, the birth of stars from gas clouds, the evolution of galaxies into sparkling spirals. Those pieces are beautiful, logical, inspiring, but the initial moment remains a forbidden zone, where physical laws evaporate like morning dew under the sun. The question is not just mathematical, but deeply philosophical. If physics did not exist at the start, what caused the universe to emerge from nothingness? Why is there something instead of absolute nothingness, an eternal silent void? In the shadows of those questions, scientists whisper to each other, voices full of hope and awe. The Big Bang is not the beginning, it is a transition, an emotional leap from the old to the new. And what existed before is more beautiful and stranger than humanity's wildest dreams, igniting in us a faith that the universe is always ready to reveal secrets for us to discover. To expand on this, recent advancements in 2025, as reported in scientific publications like Big Think and phys.org, reinforce these ideas. For instance, numerical relativity, a computational method using supercomputers to simulate Einstein's equations in extreme gravity, has been proposed by researchers such as Eugene Limit, Katie Clough, and Josu Orikoetsia to probe what happened before the Big Bang. This approach allows scientists to model chaotic, non-uniform conditions without assuming the perfect symmetry of traditional theories, potentially revealing signatures of cosmic bounces or multiverse collisions. Such simulations could confirm or refute ideas like eternal inflation, where our universe is just one bubble in an ever-expanding multiverse, each with its own Big Bang. In 1981, Alan Guth, a young physicist at the Massachusetts Institute of Technology, with an imagination exploding like the universe he described, ignited a new flame in cosmology, a flame full of inspiration that stirs countless hearts. He proposed a bold, poetic idea. Before the hot Big Bang, the universe underwent an explosive expansion phase called cosmic inflation, like a cosmic wind inflating everything to colossal scales. In a fraction of a second, a brief moment holding infinite power, space doubled, then doubled again, at least 80 times in succession, faster than the speed of light, leaving us in awe of the cosmos's grandeur. This idea solves a persistent mystery, one that makes us ponder the universe's harmony, the cosmic microwave background. The lingering echo of the Big Bang, like an ancient melody, has a nearly uniform temperature to 0.7 degrees above absolute zero, despite space regions separated by billions of light years, like distant friends who have never met yet share the same heartbeat. How could they share the same temperature if they never interacted, never exchanged energy across the vast expanse? Inflation provides an inspiring answer. Before the explosive expansion, these regions were close together, blended in thermal equilibrium, like seeds nestled side by side in the soil. Then inflation tore them apart, faster than light, leaving traces of an ancient era, a frozen memory that moves us with the universe's subtlety. But what is less emphasized? What makes the story emotionally charged? If inflation occurred before the hot Big Bang, then the Big Bang is not the beginning, not the creation from nothingness, but part of a longer journey. Something existed before an inflationary phase of indeterminate duration, perhaps a fleeting fraction of a second, or billions of years, a period where the universe quietly expanded in cold emptiness, near absolute zero, like a deep sleep before awakening. The inflating universe was not scorching or dense as we imagined. It was frigid, empty, silent, containing only a mysterious vacuum energy, an energy that does not fade. As space expands, it persists, driving ever faster growth, like an endless flow of cosmic vitality. Visualize a cosmic silk sheet, smooth and infinite, stretching in all directions at once, flattening every wrinkle, erasing every flaw, transforming any prior chaotic, disordered state into a uniform, perfect space ready for the birth of stars and galaxies. That is what inflation does to space itself. A grand artist leveling the cosmic canvas, preparing for the next strokes. Then, like a symphony shifting to a dramatic crescendo, the miracle happens. The inflationary energy transforms, decaying into particles and radiation, flooding the universe with searing heat, like a flame erupting from ashes. That is the hot Big Bang, not creation from zero, but an emotional phase change, like liquid water freezing into glittering ice under sunlight, or a seed sprouting from cold soil, carrying hope for new life. The universe does not arise from nothingness. It rebirths from a prior state, a transition that astonishes us with nature's elegance. This theory is not based on vague philosophy or fanciful dreams, but on solid evidence that moves us with science's beauty. The galaxy models we see today, sparkling spirals, gas clouds birthing new stars, match inflation's predictions perfectly, like a painting drawn by the cosmos's invisible hand. Tiny fluctuations in the cosmic microwave background temperature, measured precisely by satellites like Planck and ground-based telescopes, map quantum ripples from the inflationary era. Ripples stretched to cosmic scales, becoming seeds for all structures we see today. The flatness of space, the even distribution of matter, the absence of strange defects, like magnetic monopoles, all sing inflation's song, an inspiring hymn to the universe's harmony. And in 2025, the evidence grows even stronger, filling us with hope for upcoming discoveries. New data from the James Webb Space Telescope has brought the first images of primordial galaxies, structures seeded by quantum vibrations during inflation, confirming the theory with unprecedented accuracy, showing the early universe formed faster than we thought, with youthful galaxies glittering like newborn stars. This means the universe existed before the event we call the Big Bang, in a different physical state, a cold, expanding, mysterious realm where vacuum energy dominated like an undying flow. And that raises a bigger question, one that stirs the heart. If inflation laid the foundation for the hot Big Bang, what laid the foundation for inflation? The cold, empty, expanding space came from where? The answer takes us beyond standard cosmology, into territory most scientists avoided for decades. But now, with fresh developments in 2025, it becomes the focus of inspiring exploration. In 2003, scientists made a discovery confirming inflation and proving something existed before the Big Bang. They analyzed data from the Wilkinson Microwave Anisotropy Probe, a satellite mapping the oldest light in the universe, and found long-hidden patterns. The cosmic microwave background holds tiny temperature oscillations, some on scales smaller than the distance light could travel since the Big Bang. Sub-horizon oscillations, but super-horizon oscillations, on scales larger than our universe's horizon, could not exist unless something happened before. Imagine two people on opposite sides of Earth trying to coordinate. Without communication they cannot. Similarly, space regions beyond each other's horizons cannot synchronize properties. Yet, they did, like a cosmic miracle full of emotion. The pivotal plot showed correlations between temperature and polarization in the cosmic microwave background, with a clear dip on large scales, matching inflation perfectly and contradicting the old Big Bang model. A universe starting from a singularity would yield flat, random data. But one through inflation shows exactly what we observe, a correlation pattern reflecting a pre-Big Bang state. The Planck satellite later confirmed with higher precision, and by 2025, data from new missions like Lightbird, preparing for launch, promise to clarify these super-horizon oscillations further, bolstering inflation's case with subtle observations of primordial gravitational wave polarization. These super-horizon fluctuations are real, robust, undeniable, like whispers from the past echoing through time. In simple, inspiring language, this means information from before the hot Big Bang persists, leaving imprints on today's universe, like beautiful scars from a long journey. Those oscillations became galaxies and stars, originating from inflation quantum ripples stretched to cosmic scales by exponential expansion, frozen in place to seed all structure. When inflationary energy decayed and the hot Big Bang began, those frozen patterns remained, evolving but not forgetting their origins, making today's universe a direct descendant of the pre-Big Bang state. This evidence is so strong it has been compared to a Nobel Prize, one of modern cosmology's most significant confirmations. And in 2025, new studies from European groups are exploring how gravitational waves might complement inflation, creating a new model where waves replace the inflattened field. Challenging but enriching the picture we are painting. However, most people have never heard of it, like a cosmic secret waiting to be uncovered. Media tells of mapping the infant universe with colorful images of temperature variations, but they miss the deeper story. We have detected something from before the Big Bang, a whisper from an ancient era, echoing through time. The hot Big Bang did not erase the past, it transformed it, leaving emotional fingerprints. This tells us the universe has a history extending into the past, and if we can detect traces of the prior era, perhaps we can uncover what it was like. But what comes next is even stranger, more inspiring. The inflationary period has redefined our understanding of the universe. Before 1981, we thought the universe began hot and dense. We were wrong. Evidence now confirms that before the heat, there was cold. Before density, there was emptiness. The universe before the Big Bang looked nothing like after. Near absolute zero, empty, silent, dark, not the darkness of night, but the absence of everything. No stars, no atoms, no particles, just the fabric of space carrying mysterious energy, causing it to expand. This energy, called the inflattened field, permeated every point, not diluting as the universe grew, but maintaining constant density, making total energy double as space doubled, a phenomenon that sounds like magic, but is required by the equations. Where did this energy come from? That question leads us into the deep waters of quantum physics, where the vacuum is never truly empty, but bubbles with fluctuations, virtual particles appearing and disappearing, fields oscillating like hidden waves beneath a calm ocean. In inflation, vacuum energy dominated, like a tightly coiled spring in a high-energy state, rolling to a lower one, driving exponential expansion, doubling every tiny fraction of a second. 80 doublings sound modest, but mathematics reveals the power. Starting from grapefruit size, after 80 times, it exceeds the observable universe, an extreme expansion erasing most prior structure, leaving only quantum fluctuations amplified into today's patterns. Scientists calculate inflation lasted at least enough for 80 doublings, but possibly longer, even billions of years, an eternal period that moves us with time's infinity. We do not know what ended inflation. The inflattened field decayed, shifting states like a ball rolling downhill, stored energy converting to particles and radiation, heating space to extreme temperatures, like a frozen lake suddenly melting and igniting. That is the hot Big Bang, an inspiring awakening from cold hibernation to quark, electron, photon plasma. The Big Bang is not the start, it is the awakening, allowing particles to form, forces to act, evolution to begin, reshaping cosmology's central question. No longer what caused the Big Bang, but what caused inflation, a question leading to stranger, more inspiring theories. To understand inflation's extremity, consider exponential growth, not linear, but doubling, like a penny doubling to 2, 4, 8, reaching over $2 million by day 28, over 200 billion by day 38, exceeding Earth's wealth by day 64. The universe underwent at least 80 doublings during inflation, in an incomprehensibly short time, where human intuition fails, like taking a fist-sized balloon. After 10 doublings larger than a house, 20 larger than Earth, 40 beyond the solar system, 80 dwarfing the observable universe, that is the expansion of space itself, not matter pushing out, but coordinates stretched billions of light years, carrying quantum fluctuations from subatomic to galactic scales, turning quantum randomness into the universe's inspiring architecture. But there is a concerning implication. If inflation expanded space so vastly, the universe we see is only a tiny part, the whole much larger. Light from most never reaching us. We live in a small bubble, unaware of the greater reality. Some scientists suggest inflation has not fully stopped, continuing in most regions. Our observable universe being where inflation ended 13.8 billion years ago. But elsewhere space doubles, creating new bubble universes, each isolated eternal inflation, implying universe creation is ongoing. New universes bubbling from the inflated background, each with different properties, laws, constants. We live in one of infinite possibilities, making the question of beginnings urgent. If eternal inflation is true, our Big Bang is not the first, but one event among countless, marking a local start, not all reality. In 2025, new models like the Horizon model use entangled qubits to describe inflation as a white hole model, resolving the cosmological constant problem by balancing vacuum energy density, adding depth to eternal inflation. If eternal inflation, where did it begin? Was there a start or always existence? If time emerges from inflation, this is not just philosophy, but a testable scientific question. Models of microwave background fluctuations carry information. Future observations might reveal if eternal inflation is real, if the universe is one or among many. Currently, we know inflation is real. Evidence confirms it, pushing the origin question beyond the Big Bang into territory we are exploring, full of inspiration. This is the trillion-dollar question, one that moves us with the cosmos's grandeur. Inflation requires enormous energy to stretch a small region into the observable universe. Where did that energy come from? The answer challenges intuition. In everyday life, energy is conserved, but general relativity changes the rules. As space expands, energy increases because space carries energy. In inflation, total vacuum energy doubles as space doubles, sounding like magic, but permitted, since gravity has negative energy, balancing the universe's total energy to zero. Like a credit card charging, but debt rising accordingly. The universe has nearly exact flat geometry, total energy near zero. We live in a free universe. But what started the inflated field? Some propose quantum fluctuations from prior space-triggered inflation. Others eternal inflation extending backward. An appealing idea is inflation began from quantum uncertainty. Vacuum tunneling from low to high energy, quantum tunneling from nothingness, not absolute nothingness, but the lowest quantum allowed state, with geometry and fluctuations. Alexander Vilenkin developed the mathematical description, probability low, as in an infinite multiverse it occurs. In 2025, new studies from phys.org and Science Daily propose alternative models, where gravitational waves, instead of the inflated field, drive early expansion, based on Einstein's forgotten ideas, challenging traditional inflation, but opening new ways to understand vacuum energy, with potential to resolve the Big Bang crisis by eliminating the singularity without inflation. Other physicists are skeptical, arguing tunneling requires time, but time emerges during inflation. Physics becomes mystical, demanding questions at science's boundary. We know for sure inflation drew energy from the vacuum, converting to particles and radiation in the Big Bang, energy powering the sun, galaxies, life. We are made from empty space's energy, atoms in our bodies tracing back to that conversion. If vacuum energy can fuel inflation, what else can it do? The question leads to the strangest proposal. In 1983, Stephen Hawking suggested the universe has no beginning, not because eternal, but the question of beginning is meaningless. Time curves eliminating boundaries, using imaginary time from quantum mechanics, where time behaves like space, no special starting point. Near the Big Bang, time shifts from imaginary to real. The distinction vanishes. The universe has no edge, no start, like Earth's surface travel north to the North Pole, no farther north. Asking what lies north of the North Pole is meaningless. Hawking argued time's beginning is similar, elegantly avoiding the singularity if true. The question before the Big Bang is meaningless, Because linear time did not exist, the proposal is mathematically beautiful, resolving conceptual issues, but makes few testable predictions. We do not observe imaginary time. Hawking worked with Jim Hartle on the no-boundary proposal, the universe finite in time, but without a starting point, like a sphere finite without edges. Critics say it does not answer, but redefines, asking why this shape. The mystery remains. However, the proposal is valuable, showing intuition fails at extreme scales. Time is flexible, can transform. If Hawking is right, before is meaningless, but most physicists think there is more. Developing other theories. Roger Penrose, Nobel laureate for singularity work in black holes, proposes conformal cyclic cosmology, where the Big Bang, the end of a prior universe, cycles continuing forever. Countless universes emerging from the death of the previous. The idea is intuitive. Imagine the far future. Trillions of years hence, stars die, matter swallowed by black holes or dispersed. Black holes evaporate via Hawking radiation, leaving empty space with photons. Without mass, no natural scale. Time and distance lose meaning. The final state mathematically transforms into a new beginning. The universe does not end in a crunch, but smoothly transitions to a start. Solving the low entropy at origin, the late universe becomes smooth after decay. Penrose claims to find remnants in the cosmic microwave background, concentric circles, hot spots from prior universe black hole radiation, called Hawking points. But the community is unconvinced. Analyses show random patterns, no statistical significance. A lesson in data: the cosmic microwave background is complex. Search enough and patterns appear, but rigorous statistics deny. Penrose's theory is weak, not matching super-horizon fluctuations fitting inflation, though conceptually appealing with an eternal universe cycling through birth and death. In 2025, with potential crises in the Big Bang from Ian essays, cyclic ideas are reconsidered, but evidence still favors inflation. Black holes might hold secrets from before the Big Bang, as Penrose proposes, with Hawking radiation from prior universe supermassive black holes compressed into bright points. Hawking radiation. Black holes are not fully black, emitting particles due to quantum effects near the event horizon, slowly but eventually evaporating, final moments exploding. If occurring at a universe's end, flashes transition to the next cycle, leaving circles on the cosmic microwave background. Penrose claims to find them, but reanalyses show randomness. Other looking effects vanish. A data cautionary tale. Searching the whole sky finds coincidental circles. It does not mean prior black holes do not exist, but no evidence. Other ideas. Gravitational waves from black hole collisions propagate through transitions. Galaxy spins carry memories, no strong support. The core issue. Signals must pass through the violent shift from cold vacuum to hot plasma, possibly destroying information. The universe forgetting its past, but the search continues. New telescopes, like Euclid mapping billions of galaxies, sensitive detectors like LISA detecting primordial gravitational waves, might find pre-Big Bang traces. Currently, evidence points only to inflation as the prior state. No cyclic matter. Black holes are gravitational powerhouses, bending spacetime extremely. If anything carries information through transitions, they are candidates, but wishing them as time capsules does not make it so. Further theories. Our universe exists in unperceived extra dimensions. The Big Bang, a higher dimensional event. Conformal cyclic cosmology faces bigger issues than lacking Hawking points. It does not explain entropy. Entropy always increases per the second law of thermodynamics. Each cycle higher entropy. More disordered universe. Penrose avoids by information loss in black hole evaporation, but violates quantum mechanics. Most think information conserved. Another problem. Massive particles must decay. Protons decay. Experiments limit proton life over 10 to the 34th years. Electrons stable. Penrose relaxes later requirements, but makes the theory less predictive, adding flexibility code for adjustable parameters. Philosophical critiques. Even if working, no ultimate answer. Regressing infinitely. Explaining in circles. Inflation avoids explaining smoothness and flatness without prior cycles, specific predictions matching observations, linking particle physics. The unflattened field may be real, testable, predicting primordial gravitational waves. Experiments search for polarization signatures in the cosmic microwave background. In 2025, with new models from IA.TV on gravitational waves, holding the key to the early universe, inflation remains standard, earning its place through evidence. It does not mean cyclic is entirely wrong. Revised versions might work, but need problem solving, testable predictions matching data better than inflation. Presently, discussing before the Big Bang means inflation, a cold vacuum expanding exponentially, where evidence points. However, other ideas from string theory and extra dimensions, reality may have more dimensions than the three space and one time we experience, not science fiction, but a serious possibility from string theory, unifying quantum and gravity. Strings vibrate instead of point particles, tiny at 10 to the minus 35 meters. New physics emerges. Space as 10 dimensions, 3 visible, 1 time, 6 compactified small. Extra dimension shapes matter, determining particles and forces. The landscape of shapes vast, perhaps 10 to the 500 possibilities, each corresponding to different universes with varied laws. Our universe might be on a brane floating in bulk dimensions. We trapped on the brane, but gravity not. Explaining gravity's weakness, gravity leaks into extra dimensions, diluting, while other forces confined to the brane. The Big Bang is not the bulk start, only our brains. Something existed in the bulk before, other brains, other universes, higher dimensional reality, like video game characters, their world all, but players and computers exist outside, higher dimensions unperceived, speculative, no experiments detect extra dimensions. The Large Hadron Collider searches, finds none, dimensions too small or interactions weak, but mathematics compelling. String theory decades old, elegantly unifies forces, possibly quantum gravity theory, if true. Extra dimensions exist, complicating the Big Bang story. In 2025, with research from Science Direct on kappa deformed theories, kappa exponential inflation, integrating extra dimensions into inflation, expanding models. What happens next is more astonishing. If our universe is a brane in higher dimensions, are there other branes, other universes existing alongside, separated by tiny and noticeable distances? Yes, in brane scenarios, the bulk contains multiple branes, each a separate universe with own space-time matter. We do not see, because light trapped on brane. Photons do not jump bulk, but gravity different, fully in bulk, traveling between branes, linking separate universes. Picture parallel paper sheets floating in a room, beings on one sheet unseen by others. Light travels only on surface, but warping felt through gravity. Setup allows possibilities. Gravity strength depends on distance to other branes. Dark matter, perhaps normal matter on nearby brane pulling gravitationally, but invisible. Idea not mainstream, but illustrates scope. Bulk has own physics. Fields, particle structures unimaginable. Our brain embedded in larger reality, like a photo in an album, only see our page, but album holds many. The Big Bang, not albums start, only our pages. In brain cosmology versions, brains move in bulk, approaching collisions, releasing huge energy. Ekpyrotic scenario from Paul Steinhardt and Neil Turok. Imagine two brains moving toward each other. Gravity intensifying. Small ripples forming quantum fluctuations. Collision. Kinetic energy transfers to particles, radiation. That is the Big Bang. Our universe not from nothingness, but from prior brane collision. Cold space before collision is inflation. Hot dense after is hot Big Bang. Violent but finite transition. No singularity. After collision, branes bounce apart, separating, expanding, cooling, then approaching again. Cycle repeats. This is elegant, providing specific mechanism for Big Bang, explaining low entropy collision smooths irregularities, naturally connects string theory, branes from higher dimensional math, but theory problems, transition from collision, extreme energy, chaotic space, To observe smooth hot Big Bang, math difficult. Calculations show instabilities, creating non-uniform universe. Physicists refine models, adding new fields, tuning some work better, but not satisfied. Ekpyrotic promising, but no definitive evidence. Proof. Models primordial gravitational waves inflation predicts strong. Ekpyrotic weak. Future experiments measuring cosmic microwave background polarization test. Currently, brain remains theoretical. Beautiful math. From Greek ekpyrosis, meaning conflagration, universe destroyed by fire. Philosophers believed cosmos burns reborn from ashes. Physicists borrow 4 collision model. Collision intense. 2 brains approach through bulk, nearly flat empty. Only vacuum on surfaces. As close, gravity surges. Small wrinkles amplify seeds for structure. Collision stretches infinite decimals. Brains stick, kinetics convert to heat, temperature soars. Energy condenses into particles, quarks, leptons, photons. Pure energy floods brain, condensing uniformly, because collision everywhere simultaneous. No center edge, sea of particles, homogeneous temperature astonishing the hot Big Bang. No singularity, but shift from cold to hot. After collision, brains rebound, separate, space expands, particles cool, protons electrons combine atoms, gravity pulls atoms into clumps. Into stars, galaxies, everything we see from collision and subsequent expansion. But intriguing, brains do not separate forever. Slow, stop, approach again, gravity pulls back, cycle repeats. New collision, new Big Bang. Eternal rhythm of creation destruction. Model solves issues. Uniformity, because collision resets. Erasing complex structure starting fresh. Flatness, because geometry favors flat brains. No magnetic monopoles, because low temperature collision does not produce. Makes Big Bang less mysterious, collision understandable. Happens in particle accelerators, asteroid impacts, normal physics scaled cosmically. But weaknesses. Smooth transition. Equations predict instabilities. Density variations creating inhomogeneous universe. Proposals add supplementary fields to smooth, but increase complexity. Entropy. Each cycle increases total entropy. After many chaos, but observations show primordial, order high. How collision resets entropy. Not fully solved. Some claim information lost in collision, others quantum effects not convincing. Time, cycles eternal past, beginning or always. If always, why this structure? Similar problems as other cyclic models. Despite challenges, ekpyrotic actively researched. Serious alternative to inflation. Grounded in string theory. Correct undetermined by observations. Smoking gun models primordial gravitational waves. Different from inflation. Model says Big Bang not start, but collision. Other approaches. No need exotic extra dimensions brains. Back to basics, quantum and general relativity. To pillars modern physics incompatible. Loop quantum gravity combines by quantizing space, not continuous, but discrete. Space atoms tiny 10 to minus 35 meters, Planck length, below scale, geometry distance break. This matters for Big Bang, because singularity demands infinite small region. But minimal space cannot shrink to zero. Loop quantum gravity predicts density rises to maximum. Then gravity reverses at high density. Quantum effects create repulsion. Big Bang becomes big bounce. Mathematical consequence. Universe shifts from contraction to expansion smoothly. Prior to bounce like ours, classical spacetime, stars, galaxies matter, but collapsing. Everything falling in. Galaxies approaching. Space shrinking. Density rising. Then bounce, quantum reverses. Expansion begins. Prior universe lasted billions years. Own history structure. But most lost bounce creates amnesia universe. Extreme conditions scramble information. Only broad features survive. Like compressing image losing resolution. Left with blurry outline. Computer simulations confirm. Quantum fluctuations spike during transition. Wiping ancient classical information. Emerging expanding universe, low entropy initial conditions. Uniform density. Small quantum fluctuations exactly observed. Notably, Loop quantum gravity needs no fine-tuning. Conditions emerge naturally from bounce, creating universe ready for structure, stars, planets, life. But catch, not every contracting universe leads good bounce. If certain properties, bounce fails, chaotic state. Contracting universe must smooth classical Y. If so, infinite regress. Some argue only one bounce, single cycle, prior contraction phase had inflation or other state. Others multiple bounces, each resetting conditions, stabilizing model. Math unclear, needs more work. With confidence, loop quantum gravity provides mechanism avoiding singularity. Big bounce prediction from applying quantum to geometry. Something existed before Big Bang. Contracting universe reaching maximum density rebounding. Loop quantum gravity predicts before our expansion was contracting universe. Not mirror image, but classical per general relativity. Stars shining, galaxies forming. After collapse inward. If dark energy weakens, sign change. Gravity takes over, contracting. Initially slow. Stars burn, orbits normal. Life unnoticed. Over billions years, galaxies closer, night sky brightens. Eventually merge. Cosmic microwave background from distant past becomes from distant future. Strange thermodynamic reversal, but math consistent. Contraction continues. Gas heats, stars collide, black holes merge, temperature rises, atoms break, electrons strip, matter plasma reverse. Big Bang process. Heating destroys structure. Nuclei melt, protons, neutrons dissolve, quarks, gluons, quark soup, density high. General relativity predicts singularity, but loop quantum gravity counters. Before forming, quantum effects take over, quantum geometry resists crushing. At density near Planck 10 to 94 grams per cubic centimeter, repulsion activates, space no longer compresses, collapse halts, reverses, bounce occurs, universe expands again, that is ours. Big Bang reversal, not creation, but rebound from maximum compression. Primordial hot dense state bounce aftermath. Space expands, density drops, temperature falls. Particles condense from quark soup, nuclei form, atoms shape, stars ignite. But structure from contraction, erased. Bounce destroys, complex details torn by quantum fluctuations, information scrambled as expansion starts. No traces specific objects, only statistical properties survive. Total energy, curvature, fluctuation distribution setting initial conditions, determining fast expansion, dense matter, lumpy distribution. This is both disappointing and necessary. Disappointing because no learning prior era. Necessary because if information survived too much, our universe determined by arbitrary past, not laws. Amnesia allows new cycle develop own dynamics. Picture clear. Before Big Bang, universe with space-time matter, evolving to collapse, from which we emerge universe with amnesia. Mathematical result. When computing information through Big Bounce, most lost. Transition erases past. We cannot know full details before. Amnesia from quantum fluctuations. Bounce. Planck density. Space lattice quantum geometry chaotic. Anything passing scrambled. Like sending message infinite noise channel. Destroying most. Only unerasable parameters survive. Total energy. Space flatness curvature. Spectrum fluctuations, not specific arrangements. Martin Bajoul proved loop quantum cosmology equations contain extra parameters, some relevant before bounce, others after, not determining each other. Information lost. Profound implication. Speculate before bounce, but not certain. Build models conjecture-based, but no definitive answers from data past hidden behind impenetrable barrier. Some see limitation. Wanting full history. Amnesia denies, drawing knowledge boundary unapproachable, frustrating. But others see necessary, for science function if details determine prior cycle. Explanation requires prior cycle explanation. Endless chain. No fundamental solution. Amnesia cuts chain. Our universe understandable own terms, emerging from pre-bounce, but state not dictating micro-present, only broad conditions. Everything since follows laws, like human memory, not remember every detail, only highlights, forgetting not flaw but feature, avoiding overwhelm. Universe forgets details, remembers essentials. Forgetting degree depends, bounce duration fast erases more than slow. Current calculations bounce extremely short. Less Planck time, implying maximum amnesia, near total memory loss. But catch, information survives unexpectedly. Polarization patterns, gravitational waves, subtle correlations, galaxy distribution, higher order effects. Future observations might find hidden memories, breaching amnesia barrier, revealing glimpses pre-bounce universe. Presently conclusion, we live universe past forgotten. Big bounce resets clock. Whatever before lost only preserved rough outline. That price avoiding singularity universe survives crisis, but forgets how it got there. Question before unanswerable. Not exactly. Still ask what kind universe leads observed conditions. Use physics narrow possibilities. Test models data. But no certainty past partially hidden. Amnesia ensures mystery forever beyond reach. Inflation poses a beautiful problem, elegantly confirmed by observations. Once started, it may not fully stop. Most regions continuing forever, creating new universes endlessly, and infinite multiverse bubbling from eternal expansion. Not speculation, predictions, simple inflation models. Inflation ends when inflattened field decays low energy, but decay random, triggered quantum fluctuations, transitioning regions before others. When region transitions, becomes bubble universe hours observable. One such bubble, outside bubble, inflation continues, space doubling, other bubbles forming, each own Big Bang, bubbles causally disconnected, no signals travel, expanding away faster light. Process never stops, inflation continues somewhere. New bubbles form. Inflattened regions grow faster than bubble formation. Eternal multiverse infinite. Alan Gore and Andre Lind developed 1980s, called eternal inflation. Initially strange, but equations show generic, avoiding fine-tuning demands. Implication before Big Bang. Our hot Big Bang, not everything starts. Event in endless sea. True beginning, if any, occurred when inflation first began, pushed infinitely far past or eliminated. Some versions eternal past. No beginning, tracing timelines backward infinite. No initial moment. Other versions have beginning, inflation from initial conditions, quantum fluctuation, or other phase transition. But beginning pushed higher level, ask, when multiverse began? Perhaps unanswerable, because multiverse creates time. Multiverse challenges interpretation. If infinite universes, anything happens somewhere, universe you chose differently, Earth not forming, laws varying. Every possibility realized infinitely, making prediction hard if predicts everything. Some use anthropic reasoning. Only observe universes, allowing observers exist, selecting multiverse subset. Observations bias toward life-friendly regions, but explanation unsatisfying. Replacing sharp predictions, probabilistic selection. Others say multiverse unscientific if cannot observe other universes, untestable. Metaphysics, not physics. No observable predictions falsifiable. Theory explaining everything explains nothing. Criticism valid. Science-based testability, ideas beyond experiment philosophy, though mathematically beautiful. However, eternal inflation, not ad hoc. Emerges equations explaining observed universe theory, predicting galaxy patterns, also predicts multiverse, hard separate. Accepting inflation may entail eternal inflation. Rejecting requires explaining why inflation stopped everywhere simultaneously, demanding fine-tuning. Here multiverse issue. Successful theory leads conclusions challenging science foundations, making our universe one among countless. Existence arbitrary. Shifts question before Big Bang to entire multiverse, perhaps forever unanswerable. If multiverse exists, each bubble different laws, not drastically different from underlying theory, but enough electron mass varies. Stars burn differently, atoms not form. Variations from vacuum landscape, possible string theory. 6 extra dimensions compactify many ways. Each configuration different particle physics. Shapes determining masses, interactions. Number shapes vast, 10 to 500 or infinite. Each corresponding different vacuum not empty. but low energy field configuration. Our vacuum electron light, proton heavy, gravity weak. Other vacuums values differ. In inflation, different bubbles settle different vacuums. In flattened decay chooses randomly quantum fluctuations. Multiverse samples entire landscape. Consequences significant. Our physical properties not fundamental, but environmental. Like planet temperature varies, but thermodynamics universal. Similarly, particle masses, force strengths vary universes. String theory fundamental universal. Resolves puzzles. Why electron mass that? Gravity weak. Traditional physics no answer. Values arbitrary. But multiverse explains selection. We observe values allowing complexity. Other values sterile universes no stars chemistry observers. Here anthropic reasoning. We live rare bubble permitting life. Most bubbles dead. To hot cold masses wrong. Observations biased existence. Some physicists hate it, feeling like giving up instead calculating why electron mass, say could be any, we happen where right value, no prediction, but post hoc explanation after fact. Others accept. Not everything physics calculates first principles, some accidents environment like biology, predicting every tree shape from fundamental laws. Physics not predicting every constant nature. Framework fundamental. Details random. Debate unresolved. Depends whether physics should explain everything or just deep principles. If every constant derives theory, landscape fails to many unexplained. But if explains framework allowing details vary, landscape acceptable layer reality, discovering Earth one many planets. Testing hard cannot visit other universes, measure their electrons, but indirect evidence. Bubble collisions leave cosmic microwave background traces. Asymmetry anomalous regions. Experiment search. Non-found collisions rare methods insensitive or multiverse non-existent. Another test our constants distribution if landscape true. We near edge life permitting region, not center, because boundaries commoner than interiors. Preliminary studies suggest possibly true, but evidence weak. Presently question open. Physics very multiverse. Or measured constants truly fundamental. Fix deep principles, yet undiscovered. Answer reshapes reality understanding, making our universe typical special. Discovered laws universal local. Science explaining everything or just occurring structure. In quantum, nothing stable vacuum active. Particles appear disappear. Fields fluctuate. Measurements, Casimir effect to metal plates attract vacuum virtual particles. Universe quantum fluctuate. Emerge nothing like virtual particles. Idea Alexander Vilenkin supports. Universe from state no space-time matter. Only quantum laws abstractly operating. Keyword tunneling. Quantum particles surmount classical barriers impossibly. Electron tunnel wall lacking energy. Low probability not zero. Vilenkin proposes universe similarly. Transitioning nothing to something not absolute nothing, but minimal state. No classical spacetime particles, but quantum fields potential exist, laws operating. Here quantum vacuum basic most. Everything starting point emerges. Mathematics uses Euclidean time space like. Universe four-dimensional shape no boundary start. Tracing shape forward. Transitions normal time. From inside view, like abrupt Big Bang start. From outside Euclidean. No head, universe exists geometric object. Related Hawking no boundary, but different. Hawking transition near Big Bang. Vilenkin before. Tunneling creates small universe inflationary state. Exponentially expands transitions hot Big Bang. How a universe quantum fluctuation result nothing into inflation. Extremely low probability. But quantum anything not forever happens. Given infinite time opportunity. Event improbable occurs. Criticisms. Quantum needs time. Probability means before after. But if time created tunneling, saying tunneling probability means what? Vilenkin replies quantum constructs no clear spacetime. Uses Wheeler-DeWitt equation describing universe quantum state, no external time. Probabilities assign geometries no moments. Tunneling transitions between geometric states. Resolves controversial issue. Some find convincing, others skeptical. Debate touches deep quantum gravity problem. Describes system, One-time part system. Probability means no external clock. Despite tunneling nothing influential cosmology, providing framework discussing origin no singularity, connecting Big Bang fundamental quantum process, suggesting universe no miraculous mystery, natural quantum consequence applied gravity. But quantum puzzle another. Vacuum has energy, strange property not empty, but weighs something. Even removing particles radiation fields, vacuum has energy, exerts pressure, affects expansion called dark energy, 70% existence, but paradox, calculating vacuum energy, using quantum field theory, value huge 10 to 120 times observed worst prediction physics history, off 120 orders. Why wrong? Unknown. Each field contributes vacuum energy electron quark photon quantum oscillations ground state, some enormous, but observed small near zero. What cancels most? Some propose supersymmetry. Each particle superpartner opposite statistics. Contributions cancel. Energy reduces zero or near. But Large Hadron Collider no supersymmetry finds, at least accessible energies if exists, heavier than create now, making cancel mechanism less appealing. Other ideas relate string theory landscape. Vacuum energy many values depending vacuum. Most large, but some small we live small vacuum energy universe, because only then structures form. Large prevents galaxies. Again anthropic reasoning. Value because otherwise not here measure. Controversial explanation. Not calculate, but select from possibilities many find unsatisfying. Wanting theory predict not say anything. However, vacuum energy real. Measured effects universe accelerating. Galaxies receding faster. Acceleration requires something pushing space out. Vacuum energy. Acting cosmological constant Einstein introduced, then discarded after correct. In inflation, vacuum energy large, dominates, drives exponential expansion, then decays transfers particles radiation most gone, but small remnant remains, dark energy. Why left over? Why not exactly zero? Here cosmological constant problem. No good answer. Value observed small not zero. About 1 particle per meter random. No natural scale explains. Some think solution requires new physics gravity modifiers large scales. Dark energy vacuum. But new field. Calculations wrong misunderstanding quantum field theory curve space. Active research area. No consensus. Relates before Big Bang. Everything. Vacuum energy drives inflation. Creates prior state, if not understand, not fully understand inflation. Universe origin tied unsolved puzzle. Cracking vacuum energy paradox might reveal where inflation from, why started, eternal inflation, or beginning. Presently live mystery empty space has energy, smaller predicted. Energy perhaps responsible creating universe as no. Understanding before Big Bang requires solving Einstein equations, extreme conditions, analytical methods fail. Math impossible. Infinities appear. Approximations break. Only way compute brute force numerical relativity. Using supercomputers simulate gravity harshly. Huge challenge. Einstein equations 10 partial differential equations nonlinear coupled. Simple situations solvable pen paper. But high curvature quantum effects important no symmetry. Needs computers. Large computers run weeks months crunch number solutions. Eugene Limit. Katie Clough Joe Sewell Roscoe published 2025 outlining numerical relativity exploring pre-Big Bang physics. Arguing inflation before misunderstood, without computational methods equations complex. Conditions harsh, needs simulations. Propose starting initial state before inflation, no assuming smooth symmetry, allowing bumpy chaos, evolve forward using full Einstein plus quantum corrections, see happens, inflate, collapse, surprise, radical approach no assuming answers, most models assume homogeneity simplifying math, but perhaps wrong, universe before inflation extremely inhomogeneous, numerical relativity handles. No symmetry assumptions. Simulations test otherwise inaccessible scenarios. Brain collisions. Big bounce complex prior states. Cyclic cosmology. Multiverse collisions each equations. Run simulations. Compare output observations. Some survive, others fail. Science progresses when theory insufficient. But obstacles, computational cost. Full quantum gravity simulations demand almost non-existent resources. Current supercomputers struggle. Future possible. Progress making. Better algorithms. Efficient code. Faster machines. Decade. Simulations feasible. Another obstacle. Knowing simulates what need initial conditions, but unknown prior Big Bang state. Try different scenarios. Possibility space huge. Computing power limited. Cannot simulate everything. Choose wisely. Despite numerical relativity successful. Other fields. Simulating black hole mergers. Predicting gravitational wave signals. LIGO detected. Excellent match. Proves method works. Handles strong gravity. Makes testable predictions. Applying cosmology. Natural black holes. Big Bang related extreme curvature. Similar techniques. Related physics. Research developing methods including quantum effects. Hard. Quantum field theory. Curved background notoriously difficult, but progress. Effective field theory methods allow approximate quantum corrections. Loop quantum gravity. Discrete space framework. String theory. Separate computational techniques. Combining provides window into pre-Big Bang. Not perfect, but glimpse, suggestions, models consistent or contradictory observations. Real progress. Hope 10-20 years. Limited pre-Big Bang simulations, excluding theories, supporting others. Narrowing possibilities. Not final answer, but significant advancement. To test before Big Bang. Need observations. Signals from era. Imprints existing today's universe, but detecting demands cutting-edge tools, sometimes beyond. Here search. Primordial gravitational waves. Space-time ripples from inflation. Exponential expansion. Quantum fluctuations. Gravitational field amplified. Real waves. Wavelengths spanning observable universe. Traveling carrying inflationary era information. Waves affect cosmic microwave background polarization. Creating B modes. Distinct E modes. Density fluctuations. Detecting B modes confirms inflation. Measures strength indicating inflationary energy scale. Density reached. Constraining prior state models. Experiment. Search B modes. Bicep Keck telescope. South Pole. Planck satellite. Future Lightbird. CMBS-4. Instruments measure polarization. Delicate precision. Mapping sky. Filtering foreground contamination. Seeking primordial signal. Buried noise. So far, no confirmed detection. Limits. Improving signal. Weaker initial estimates, indicating inflation. Low energy models predict, excluding simple strong scenarios. Remaining relevant. Complex dynamic subtle physics. Second, search deviations. Perfect scale invariance. Inflation predicts fluctuation amplitudes. Nearly same all scales, but small deviations carry information. How in flattened field evolved. Speeding. Slowing. Multiple fields or one. Precise cosmic microwave background measurements. Planck show deviations, but hint anomalies. Asymmetry. Slight hemispheres. Power deficit. Large angular scales. Perhaps noise or real signal. Pre-Big Bang physics. Third, search non-Gaussianity fluctuations. Gaussian. Random. Uncorrelated. Non-Gaussian patterns. Higher order correlations. Pre-Big Bang scenarios create different non-Gaussian signatures. Inflation weak. Ekpyrotic strong. Bounce distinct. Measuring requires analyzing billions data points. 3-4 point correlations. Higher order statistics. Huge computational challenge, but doable. Current surveys. Euclid Vera Rubin Observatory. Helion in billions galaxies. Encoding distribution. Primordial fluctuations, including non-Gaussianity. Fourth, observe large-scale structure. Galaxy distribution. Cluster shapes. Matter web. All evolves. Seeds sown. Inflation. Mapping structure. Universe history reconstructs. Seeds evolution. Testing. Understanding initial conditions. Pre-Big Bang state. Fifth, search exotic signatures. Cosmic strings. Domain walls. Topological defects. Predicted some pre-Big Bang models, but not others. Finding excludes simple inflation forms. Absence constrains phase transitions. Symmetry breakings. Fields active. Sixth, use gravitational wave detectors. LIGO Virgo Cagra detect black hole mergers. Future Lisa Einstein Telescope Cosmic Explorer. Sea waves pre-inflation era, perhaps phase transitions. Background gravitational waves carrying signatures. Testing demands patience building instruments, collecting data, careful analysis, eliminating systematics. Reward understanding. Each measurement constrains theories, narrows possibilities, bringing closer knowing before Big Bang. Their boundary knowledge. Hard limits physics imposes despite advanced tools. Information forever hidden. Understanding key limits. Tells questions answerable which not. Fundamental limit cosmic horizon light finite speed. Universe finite age. Only see objects certain distance. Observable universe 93 billion light-years radius. Beyond. Light no time reach. Unseen forever. Horizon cuts information if universe infinite. Only observed decimal fraction. Even observable universe. Information limited cosmic microwave background. Direct earliest observation. 380,000 years after Big Bang. Before, universe opaque. Photons scattered constantly. No light travels free absolute photon barrier. Cannot see earlier electromagnetic radiation. Gravitational waves penetrate deeper. No scattering matter. Principle carry earlier information. Perhaps inflation. But detection extremely hard signals weak. Frequencies inaccessible. Needs yet built detectors. Neutrinos another window. Mostly non-interacting matter. Neutrinos seconds after Big Bang travel. Cosmic neutrino background exists, but undetected energy to low. Past detectors traceless. Detection perhaps impossible practical technology. Post-bounce information problem if loop quantum cosmology true. Big bounce erases details. Amnesia built equations. No clever observation breaches information destroyed quantum level. No longer exists. No signals forward. Limit not technological but physical. Inflation similar problem exponential expansion smooths primordial structure. Anything existing before inflation stretched unobservably. Only quantum fluctuations end inflation survive. Pre-inflation erased pushed beyond horizon diluted undetectable. Cannot reconstruct pre-inflation state post-inflation observations. Multiverse if real forever beyond testing if bubbles causally disconnected. No observations. No signals cross voids. Theory no observable predictions other universes. Only see own bubble makes multiverse hypothesis unfalsifiable traditional sense. Some say not qualifying science. However, indirect tests, bubble collisions leave cosmic microwave background traces. Bruises asymmetry anomalous regions experiments search none found. Collisions rare signatures subtle or multiverse non-existent. Philosophical questions beginning also beyond observable why laws form. Why something not nothing. Metaphysical outside empirical science. Describes how universe evolves. Not why exists perhaps not scientific question. Does not mean stop asking, but honest limits. Some questions we answer, others narrow. Still others mystery not lacking ingenuity. But reality imposes knowledge boundaries. Respecting aspect humility intellectual. However boundaries shift impossible yesterday routine tomorrow. Cosmic microwave background speculated 1940s, 21st century map detail. Gravitational waves imagined 1960s. Now detected weekly. Impossible becomes possible, limits expand. Perhaps they observe big bounce. Detect primordial gravitational waves inflation. Find multiverse evidence. Or hit real wall. Asymptotic boundary no progress. Either way. Journey worthwhile each step reveals profound reality. If universe not begin Big Bang, what deeper questions mean purpose, creation, meaning? Not scientific questions, but human. Science before influences thinking. Traditional theology points Big Bang evidence creation universe beginning. Thus creator. What outside brought existence. Cosmological argument refined updated modern cosmology. But if Big Bang not start, if inflation before, universe bounce before, eternal inflation no starting point, beginning concept dissolves, universe eternal sense not unchanging, evolves phases, but no initial moment, no point everything started nothing. This eliminates need external cause, not necessarily argument eternal universe still requires explanation. Why these laws? Why this structure? Why something not nothing? Argument shifts temporal origin, logical contingency, universe depends something beyond existence, even no temporal beginning. Others argue opposite. Eternal universe needs no external cause, simply is, always existed some form. Asking why like asking why 2 + 2 = 4, not deep reason. Brute fact. Viewpoint universe self-contained, complete, no dependency. Buddhism, some Eastern philosophies align cyclic time, endless universe, arising, dissolving, ancient texts. Cyclic cosmology fits bounce, repeating cycles idea. Perhaps philosophers intuited reality, science confirms, or coincidence. Humans imagined many cosmologies, some coincidentally align. Also meaning question if universe, bubble, infinite multiverse, makes us insignificant. Relevant cosmos, mere statistical fluctuations, see infinite possibilities. Some worrying, wanting humanity important, central, special. But others embrace meaninglessness, liberating. Freeze cosmic burden, no creation point. Universe not exist as free, create own meaning. Define purpose, no cosmic validation. Existential response cosmology, science neutral. Describes what, not what ought. Physics tells universe evolves how, not live how. Separate questions demanding separate tools. Ethics, philosophy, personal reflection. Science informs conversation, not dictates conclusions. Science provides perspective, thought. Universe 6,000 years, billions. Earth center, not. Milky Way, whole universe. Galaxies outnumber. Big Bang beginning, perhaps not. Each discovery humbling, expands view, challenges assumptions, process uncomfortable, disrupts narratives, questions authority, forces rethink, but exciting. Living universe, richer, stranger than ancestors imagined. Reality boundaries, wider thought. Before Big Bang, not just physics question, but existence, nature, a find answers, reshapes philosophy, theology, understanding, place cosmos. If not find, also tells something, knowledge limits, mystery, core, everything. Either way, asking transforms, because forces confront deepest existence riddles. Why something, not nothing? Unknown. Perhaps science answers, perhaps not. But fact we ask, investigate, pushes understanding boundaries, self-remarkable. We universe trying understand itself, mission regardless leads profound humanity. 50 years ahead, change of understanding universe origins, new tools operating, experiments planned, technology advances, impossible becomes feasible. Here we might discover before Big Bang. Gravitational wave astronomy, golden age detectors now see black hole mergers. Next generation see more. Einstein telescope, cosmic explorer, space-based LISA. Detect waves, primordial universe. Phase transitions, cosmic strings, perhaps inflation. If signals exist, fine detection revolutionizes cosmology. Directly confirms inflation. Measures pre-Big Bang energy scale. Distinguishes models. Inflation versus ekpyrotic. Single versus multiple fields. Simple versus complex dynamics. Gravitational wave patterns encode information, needs sensitive detectors. Cosmic microwave background evolves, grand telescopes. Simon's Observatory. CMBS for map polarization, full sky. Space missions, Lightbird follow. Each sensitivity improvement brings closer detecting B modes. Measuring primordial gravitational wave background. Seeing fingerprint pre-Big Bang universe. Particle accelerators contribute, large hadron collider continues, new physics search. Future colliders, if built, reach higher energies. Possibly detect particles, forces, relevant primordial universe. Supersymmetry. Extra dimensions. New fields, discoveries constrain cosmological models. Connect particle physics, Big Bang. Astronomical surveys, map universe, unprecedented detail. Vera Rubin Observatory image billions galaxies. Euclid measure shapes, positions. Square kilometer array map. Hydrogen universe history surveys, test inflation. Ring primordial fluctuation spectrum. Non-Gaussianity. Scale dependence. Each measurement refines knowledge. Theoretical progress continues. Loop quantum gravity matures. String theory develops. Numerical relativity becomes feasible, new ideas emerge constantly. Some fail, some succeed. Possibility landscape narrows. Identifying scenarios fitting observations, not Artificial intelligence accelerates discovery. Machine learning algorithms analyze data faster. Humans find overlooked patterns, simulate physics efficiently. AI used detecting gravitational waves, analyzing microwave maps, spotting anomalies as improves, becomes standard cosmology tool. Quantum computing useful. Full quantum gravity simulations demand enormous power. Classical machines hard, quantum excels, handles quantum systems naturally. As scales, simulate big bounce, quantum tunneling nothingness models, explore multiverse landscape. Speculative, but plausible. Private space companies change. Gain cheaper launches, more satellites, better instruments. SpaceX Blue Origin. Others make space access routine. Experiments previously costly. Small satellites, detector constellations, new telescopes. Discovery pace accelerates. International collaboration strong. Event Horizon Telescope proves global efforts achieve. Future projects ambitious, combining worldwide telescope data, coordinating multi-wavelength observations, sharing resources. Expertise. Questions to big single nation. Collaboration essential. Decades ahead. Answers not complete. Science not provide, but significant progress. No inflation confirmed. Not. Primordial gravitational waves exist. Universe bounced or multiverse collision. Pre-Big Bang shift. Speculation established science, or find unexpected signatures. No theory predicted anomalies. Breaking models. More interesting, meaning reality stranger imagined. Clever theories missed fundamental. Discovery not always find expected, sometimes find not. Either way, future bright. Questions profound, tools improving, community engaged. Living cosmology. Golden age era. Humanity learns before Big Bang, pushing understanding existence boundaries, exploring how universe truly began. Journey continues, mystery clarifying. Meanwhile, each answer births new question, each discovery reveals new puzzle. Science nature endless frontier, always progress no completion. And that exactly should, because universe vast strange beautiful, understanding adventure greatest humanity undertakes. And in that journey, we not only discover universe, but discover ourselves, finding inspiration from cosmos gives secrets, reminding each stardust grain part us, and each question invitation. Fly farther, dream bigger, live fuller wonder existence.